NASA has confirmed a black hole feeding faster than scientists thought possible. Something massive deep in space devours matter faster than standard scientific models predicted. How can it blaze with brilliant light while exceeding theoretical limits? What hidden truth does this reveal about the universe above our heads? Stay with me. Over the next several minutes, we'll uncover exactly why this discovery has NASA's top experts working to understand, what it means for the stars you've watched your entire life, and why scientists are calling this one of the most baffling cosmic mysteries they've ever witnessed. If cosmic secrets like this make you see the night sky differently, smash that like button right now and drop a comment telling me where you're watching from under tonight's stars. You've trusted NASA's telescopes to reveal the universe's deepest secrets for decades now. You remember when Hubble first opened our eyes to galaxies beyond counting. You recall when those first images showed us worlds we never imagined existed. Well, NASA's Chandra X-ray Observatory just captured something that has their entire team of veteran astronomers surprised by the unexpected finding. Picture this moment with me. September rolled around, and the data started flowing back from Chandra's sensitive instruments, aimed at a distant corner of the cosmos. Scientists expected to see what they always see: black holes behaving according to the rules that govern everything we understand about gravity and matter. Instead, they found something eating at a pace that challenges our physics model. This isn't speculation pulled from science fiction novels. This is verified telescope data showing a supermassive black hole consuming material so fast that standard models suggest it would have dimmed significantly. But here's what stuns everyone looking at those images. The system is glowing extraordinarily brightly, contrary to predictions, blazing with energy that challenges astronomers' predictions for these cosmic giants. Think about that for just a moment. You've lived through an era when science gave us reliable answers, when experts could point to the rules and show us how the universe follows them with mathematical precision. The Apollo missions succeeded because we understood gravity. Satellites orbit because we know the physics. Everything worked according to plan because the rules held firm. Now NASA's looking at confirmed observations showing behaviour exceeding model predictions right in front of their most sophisticated instruments. The feeding rate they're measuring exceeds what scientists call the Eddington limit, a boundary so fundamental to astrophysics that textbooks describe it as a fundamental principle. Imagine watching a car engine rev past redline, not by a little, but by factors that should cause instability. Yet instead of exploding, it runs smoother and more powerful than engines operating safely within normal ranges. That's the head-scratching reality staring back at researchers from their computer screens right now. This black hole sits out there in deep space, visible only through X-ray wavelengths our eyes can't detect, pulling matter into itself at speeds that create friction and heat so intense the glow reaches across billions of light-years to Chandra's detectors. The energy signature is unmistakable. The measurements are precise. The conclusion is unavoidable. Something is happening that current models don't fully explain yet. You know how reassuring it feels when experts have answers? When the universe makes sense according to principles tested and proven over generations of scientific work? Well, that reassurance just hit a wall. Because the veteran astronomers analysing this discovery, people who've spent entire careers studying black holes and galactic evolution, are openly admitting they don't know what they're looking at. This isn't some distant theoretical problem that only matters to academics writing papers nobody reads. This discovery touches something fundamental about how matter and energy behave at the most extreme conditions the universe creates. Black holes aren't just exotic objects floating in space for our curiosity. They're the engines that shape galaxies. They influence star formation across cosmic distances. They play a role in creating the very elements that eventually form planets and, yes, even life itself. So when one exceeds predicted behaviour this significantly, it means our understanding of cosmic evolution has a genuine hole in it. Pardon the expression. NASA confirmed the observations through multiple data checks. They verified the measurements against known standards. They ruled out instrument errors and alternative explanations. What remains is a legitimate cosmic mystery staring humanity straight in the face. The discovery came from examining what astronomers call a quasar. That's essentially a supermassive black hole surrounded by a disk of material spiralling inward, heating up to temperatures that make the sun's surface look cool by comparison. Quasars rank among the brightest objects in the universe, visible across distances so vast the light we see today began its journey when the cosmos was still young. But this particular quasar caught everyone's attention because it's doing something quasars aren't supposed to do during certain phases of feeding. When black holes consume matter too quickly, The physics suggests they should become less visible, not more. The radiation pressure from all that energy release should push incoming material away, creating a natural brake on the feeding process. It's a self-regulating system that keeps things in balance. Except here's what Chandra revealed. No balance. No braking. Just relentless consumption, paired with brilliant output that grows stronger instead of dimmer. The very mechanism that should limit this black hole's appetite seems to have vanished entirely, and nobody standing at the cutting edge of astrophysics can tell you why. Does that surprise you as much as it surprises them? You've watched NASA accomplish seemingly impossible things throughout your lifetime. Moon landing, Mars rovers, telescopes peering back to the universe's birth, each achievement built on solid understanding of how nature works. But this discovery reminds us that for all our progress, the cosmos still holds secrets that humble even our best minds and most sophisticated instruments. The alert went out through NASA's communication channels, and within hours, astronomers worldwide started requesting time on other telescopes to follow up. Because when you find something that breaks the rules this completely, you don't just write a paper and move on. You gather every instrument you can point at it and try to understand what you're really seeing. That's where we stand right now, at the beginning of a cosmic detective story, where the main suspect is challenging current models and inspiring new research. What makes this discovery particularly intriguing is the confidence NASA expresses despite the mystery. They're not hedging or suggesting maybe they found something unusual. The announcement carries the weight of certainty. This black hole is confirmed to be growing out of control, confirmed to be exceeding theoretical limits, confirmed to be displaying behavior that current models cannot predict or explain. That level of scientific certainty about something genuinely unexplained doesn't come along often. Think back through the major astronomy discoveries you've witnessed across your lifetime. Each one opened doors to new understanding. Each one showed us something we didn't know existed. But how many times did experts stand up and say, "We found it, we've measured it, we've confirmed it, and we're working to understand how it operates under these conditions"? That combination of certainty and mystery is rare in modern science. It signals we're standing at one of those moments when human knowledge expands not just by learning something new, but by discovering how much we still don't understand. The telescope doesn't lie. The data doesn't fabricate itself. What Chandra captured represents reality happening out there in the universe, whether we understand it or not. And right now, reality is showing us a black hole that behaves differently than models predicted, written by decades of careful research and observation. That's not a failure of science. That's science working exactly as it should, revealing truths that challenge us to think deeper and look closer at how the cosmos really operates. So we begin this journey together with a confirmed mystery that demands explanation, a cosmic giant breaking rules with apparent ease, while NASA's best instruments watch it happen in real time. The question hanging over everything now is simple but profound. What does this tell us about the universe we thought we understood? But before we can tackle that bigger question, we need to understand exactly what makes this black hole's behaviour so impossible in the first place, and why the light it produces shouldn't exist at all during this kind of extreme feeding frenzy. Picture yourself standing outside on a clear night, gazing up at stars you've watched for decades. Those points of light seem constant, unchanging, reliable, but scattered among them, invisible to your eyes, are objects so energetic they make our sun look like a dying ember. Quasars exist in that category, cosmic lighthouses powered by black holes, consuming matter at rates that turn entire star systems into fuel. Here's what should happen when one of these giants feeds too aggressively. Imagine trying to stuff too much wood into a fireplace too quickly. The flames get choked. Smoke billows out. The fire dims under the load because you've overwhelmed the combustion process. Physics dictates a similar principle for black holes gorging themselves beyond certain rates. The incoming matter creates so much radiation pressure that it should blow away additional material trying to fall in. The system regulates itself. The brightness drops. The feeding slows. That's the expectation carried by every astronomer pointing instruments at these objects. Feed too fast, shine too bright initially, then watch everything calm down as natural limits kick in. It's a pattern confirmed by decades of observations across thousands of quasars. The universe follows this script so reliably that scientists built entire theories around it. Now imagine NASA's surprise when Chandra's data showed the complete opposite. During what should be a dimming phase, this quasar blazes brighter than standard theoretical models predict. The X-rays pouring off it carry energy signatures that indicate matter plunging inward at breakneck speeds. And instead of the expected shutdown or slowdown, the feeding continues unabated. while the light output reaches levels that make veteran researchers check their instruments for errors. You know that feeling when something familiar suddenly behaves in a way that makes no sense? When your car makes a sound it's never made before, or your body reacts differently than it ever has. That moment of confusion where experience tells you one thing but reality shows you another? That's exactly where NASA's team found themselves staring at these observations. The quasar glows in X-ray wavelength because matter spiralling into the black hole heats up to temperatures measuring in the millions of degrees. At those extremes, atoms strip apart and particles slam together with such violence they emit high-energy radiation. Chandra specializes in detecting precisely these X-rays, mapping out the intensity and distribution in ways that reveal what's happening in these extreme environments. What the telescope revealed in this case was a feeding disk blazing so intensely that calculations suggest the black hole is consuming matter well beyond what physics models predict as stable. Think of it like watching someone eat 3 full meals simultaneously while running a marathon. The energy output exceeds what models predicted. Yet there it is, happening right in front of calibrated instruments, designed specifically to measure these exact phenomena. The brightness carries information encoded in its spectrum. Scientists can analyze the light and determine temperatures, densities, velocities of material swirling around the black hole. Every piece of data contributes to understanding what's occurring at distances so vast that the light reaching Chandra today began its journey across the universe long before humans built their first civilizations on Earth. And here's what makes this particularly baffling. The spectrum shows no signs of the radiation pressure effect that should be throttling the feeding process. Imagine pressing the gas pedal in a car and expecting the engine to limit itself automatically when you push too hard. That's essentially what should happen with black holes. The radiation produced by excessive feeding should create an outward pressure that prevents more matter from falling in. It's a cosmic safety valve built into the physics. But this quasar spectrum suggests the expected safety valve isn't operating as predicted, or perhaps additional factors are at play that weren't included in standard models. The matter keeps plunging inward, the radiation keeps pouring outward, and the balance that should regulate everything appears nowhere in the data. That absence of expected behaviour is what keeps scientists awake at night, because it implies something fundamental in our understanding is either incomplete or wrong. You've lived long enough to know that surprises often teach the best lessons. That moment when reality contradicts your expectations is precisely when you learn something new about how the world actually works. Well, the cosmos just delivered one of those teaching moments to humanity's astronomers, and the lesson plan looks more complicated than anyone anticipated. Think about the implications for just a moment. If this one black hole can exceed limits thought to be universal, what does that say about the thousands of others we've observed and catalogued? Were they all operating under constraints this one somehow escaped? Or have we been looking at the data through assumptions that missed something crucial about how these objects actually behave when conditions align in specific ways? The energy streaming off this quasar during its excessive feeding phase includes not just light across many wavelengths, but also powerful jets of particles blasting outward along the black hole's rotational axis. These jets move at substantial fractions of light speed, carrying energy across galactic distances, influencing everything in their path. When a quasar misbehaves this dramatically, those jets become even more significant because they represent energy that should have been regulated but wasn't. Imagine standing near a waterfall that suddenly doubles its flow without warning. The sound changes, the spray reaches farther. The impact on everything downstream increases. That's somewhat analogous to what this black hole is doing, taking energy that should have been controlled by natural processes and releasing it into the surrounding space at rates that exceed prediction. The cosmic neighbourhood around this object is experiencing effects that models suggested shouldn't be possible at these intensities. Now here's something that really captures the mystery perfectly. The Chandra observations show this brilliant glow persisting during a phase when theoretical models predict significant dimming, not just staying constant, staying bright beyond the limits. It's as if the black hole looked at nature's rulebook and decided those pages simply didn't apply to its particular situation. The defiance isn't subtle. It's dramatic enough that researchers noticed it immediately once they examined the data carefully. Does that make you wonder what else might be happening out there that we haven't noticed yet? How many cosmic rules are being bent or broken by objects we haven't observed closely enough? The universe revealed its age to us through careful measurement. It showed us its expansion through patient observation. Each discovery built our confidence that we understood the fundamental pattern. Then something like this comes along and reminds us that confidence should always be tempered with humility about what we don't yet know. The telescope image itself doesn't show much to untrained eyes, just a bright point against darkness. maybe some structures around it depending on how the data gets processed for display. But to scientists reading the information encoded in that light, the image tells a story of cosmic rebellion against expected norms. Every photon carries information about the extreme physics occurring at its source, and the message written in those photons says something is very different about this particular corner of the universe. You remember when scientists first confirmed black holes actually existed? For years they were theoretical objects, predicted by mathematics but never directly observed. Then technology advanced enough to detect their gravitational effects, and eventually capture evidence of their presence beyond doubt. That journey from theory to confirmed reality took patience and persistence. Now we face a new puzzle. Black holes are real, their basic behaviour is understood, but this one is doing something that doesn't fit the established patterns. The brightness that should have dimmed stays strong. The feeding that should have throttled itself continues unabated. The natural balance that should regulate everything appears absent or overwhelmed, and NASA's instruments watch it all happen with the clarity that comes from decades of engineering refinement and calibration against known standards. There's no ambiguity in the measurements themselves, only in what they mean for our understanding of how these cosmic giants actually operate when pushed beyond normal limits. So we stand here together, looking at confirmed observations of a black hole breaking its diet by such dramatic margins that scientists can't explain the physics allowing it to happen. The blaze that should have dimmed burns brighter than theory predicts possible, and that impossible brightness holds clues to cosmic processes we've yet to fully understand. But to grasp why this matters so much, we need to step back and look at the balance this black hole somehow managed to overpower, the fundamental force that's supposed to keep even these cosmic monsters in check. You've watched nature maintain balance throughout your life. Rivers carve valleys, but don't empty oceans. Trees grow tall, but eventually stop. Your body regulates temperature without conscious thought. Balance appears woven into reality itself at every scale we can observe. Well, the universe has its own version of that balance when it comes to how fast black holes can grow, and understanding it helps reveal just how shocking this NASA discovery really is. Imagine water flowing down a pipe. Push it too hard and pressure builds. That pressure eventually limits how much more water you can force through, no matter how hard you push. Something similar should happen with matter falling into a black hole. The object's gravity pulls material inward with incredible force, but as that material accelerates and compresses, it heats up and starts radiating energy outward. Eventually, that outward radiation pressure should balance against the inward gravitational pull, creating a natural limit on how fast the black hole can actually feed. Scientists have a name for this limit. They call it the Eddington limit, after the British astrophysicist who worked out the mathematics describing this balance almost a century ago. The principle is straightforward. For any given mass, there's a maximum rate at which it can pull in matter before the radiation produced pushes back hard enough to stop additional material from falling in. It's nature's way of preventing cosmic objects from growing infinitely fast. Think of it like trying to inflate a balloon. At first it's easy, but as the balloon expands, the rubber pushes back harder against each new breath you blow into it. Eventually you reach a point where the resistance equals your blowing force, and the balloon stops expanding unless you push harder. Black holes face similar resistance from their own radiation when they feed too quickly. The Eddington limit describes that resistance point. For decades, observations confirmed this limit held across different types of cosmic objects. Stars have it. Black holes have it. Any massive object pulling in material from its surroundings eventually hits this balance point where its growth rate stabilizes. Observations generally aligned with this principle across many systems. Textbooks taught it as fundamental physics. Students calculated it in assignments. Researchers used it to predict how quickly black holes could grow over cosmic time. Now picture NASA's team analysing Chandra's data and watching those calculations fail completely. The feeding rate they're measuring exceeds the Eddington limit by substantial margins. We're not talking about slightly exceeding it the way you might push a speed limit by a few units. We're talking about exceeding it significantly in ways that current models don't fully account for yet. How does something this massive exceed a balance scientists thought was fundamental to these systems? That's the question keeping astrophysicists up at night right now. Because if this black hole can do it, the implications ripple through our entire understanding of how these objects grow and evolve across cosmic history. You know that feeling when a fundamental assumption proves wrong? When something you took for granted suddenly reveals itself as less certain than you believed? The Eddington limit wasn't just a guess or rough approximation. It emerged from solid physics describing how radiation and gravity interact. Seeing it exceed this significantly encourages scientists to reconsider either the observations themselves or the assumptions built into the limit's derivation. The observations, as we've discussed, passed every verification test NASA could throw at them. The telescope works properly, the calibrations check out, the data analysis used standard techniques proven reliable across thousands of previous measurements. So the observations appear sound, which means the assumptions need examining. One possibility is that some process we don't understand is allowing matter to fall into this black hole through pathways that avoid the radiation pressure bottleneck. Imagine water finding a way around that pipe restriction by flowing through channels where pressure doesn't build up the same way. If matter can approach the black hole along specific trajectories or in particular configurations, perhaps it avoids the worst effects of radiation pressure and manages to fall in faster than simple models predict. Another possibility is that the black hole's rotation plays a role we haven't fully appreciated. Spinning black holes drag space-time itself around with them, creating conditions quite different from non-spinning. Maybe at certain spin rates and feeding geometries, the rotation allows matter to spiral inward faster than the Eddington limit suggests possible. The mathematics describing spinning black holes gets complicated quickly, and there might be regimes where feeding behaviour differs from what simpler models predict. Or perhaps something about the matter itself changes the equation. If the material falling into this black hole has properties or configurations different from what typically gets modelled, the radiation pressure might not build up as expected. Think of it like the difference between liquid and gas flowing through that pipe. Different states of matter respond differently to pressure. Maybe at these extremes, matter behaves in ways that change how effectively radiation pressure can slow its inward fall. Each of these possibilities opens doors to new physics, or at least to deeper understanding of extreme conditions. And that's what makes this discovery so valuable despite, or perhaps because of, its mystery. Science advances not just by confirming what we expect, but by finding exceptions that force us to refine our understanding. This black hole just handed researchers an exception dramatic enough to demand attention. The balance we thought existed looks less like an absolute wall, and more like a speed suggestion that can be exceeded under circumstances we don't yet fully grasp. Imagine traffic laws that work perfectly in every observed situation, suddenly failing in one specific intersection. You'd want to understand what makes that intersection different, what conditions allow behaviour that breaks the normal patterns. That's exactly the investigation underway now regarding this cosmic rule breaker. Here's something worth appreciating about how science handles moments like this. NASA isn't hiding the mystery or pretending they understand what they don't. The announcement openly acknowledges this behaviour exceeds theoretical predictions. That honesty reflects the integrity at the heart of good science. Admit what you don't know. Share the puzzle openly. Invite others to help solve it. Compare that to fields where experts never admit uncertainty, where every question supposedly has a clear answer. Science's willingness to say we found something that doesn't fit is part of what makes it trustworthy over the long run. The Eddington limit didn't disappear just because one black hole exceeds it. The physics behind the limit still holds for normal circumstances. What this discovery suggests is that circumstances can exist where normal doesn't apply, where additional factors come into play that weren't included in the original calculations. Finding those factors and understanding how they modify the balance is the work ahead. Think about how many times progress came from explaining exceptions to rules. Newton's gravity worked beautifully until Mercury's orbit showed tiny deviations. Those deviations eventually led to Einstein's general relativity, which explained both Mercury's oddity and vast new realms of physics. The rule didn't vanish, it got refined into something more complete. That's the opportunity this black hole presents now. You've lived through enough history to recognise these moments when they arrive. When humanity stood on the moon and looked back at Earth, our perspective shifted. When telescopes revealed galaxies beyond counting, our sense of cosmic scale transformed. This discovery might seem more abstract since we can't see the black hole with our eyes, but it carries similar potential to shift understanding in fundamental ways. The balance we thought limited all cosmic growth appears less absolute, and figuring out why opens pathways to discoveries we can't yet predict. The calculations that predicted limits now need refinement or revision. The models that worked for thousands of observations need adjustment to account for this outlier. And through that process of refinement and adjustment, human knowledge expands into territory we couldn't even map before this observation revealed it existed. That's the gift hidden inside this cosmic mystery. Not just a puzzle to solve, but an opportunity to understand reality more deeply than we did before. So, we've established that nature's balance got overpowered. The limit that should have controlled this black hole's feeding rate appears overwhelmed by forces or conditions we don't yet understand. But the mystery deepens further when we look at what this excessive feeding produces, because the energy streaming outward from this cosmic giant is unexpected during this kind of growth phase according to current models. You know how a river flows downhill, carving through landscape, always moving toward lower ground? Energy in the universe follows similar patterns, flowing from high concentration to low, spreading out, seeking balance. Black holes interrupt that pattern by concentrating energy in ways that defy everyday intuition. And this particular black hole is concentrating energy so dramatically that it's producing fireworks when scientists expected a blackout. Picture the scene Chandra's instruments revealed. Matter spiraling inward generates friction that heats material to temperatures where atoms cannot exist in. Electrons strip away from nuclei. Particles collide with such violence they emit X-rays. Light so energetic it penetrates matter that would stop ordinary visible light cold. This radiation pours outward in all directions, and when conditions are right, some of it channels into narrow jets blasting along the black hole's rotational axis at speeds approaching light itself. These jets represent some of the most powerful sustained energy release in the universe. Not explosive like supernovas that burn bright and fade. These are steady streams of particles and radiation, maintained across thousands or millions of years, powered by the steady feeding of the central black hole. When you see images of galaxies with brilliant jets extending far beyond their visible boundaries, you're looking at black hole energy reshaping space across distances that dwarf the parent galaxy itself. Now here's what should happen, according to models built on decades of observation and theory. When a black hole exceeds safe feeding rates and pushes past the Eddington limit, the excess radiation is expected to create obscuring material around the black hole, according to standard models. Think of it like fog rolling in over a lighthouse. The light source still shines, but you can't see it clearly through the obscuring material blown outward by radiation. The black hole should effectively hide itself behind a shell of its own blown-off atmosphere. That prediction comes from solid reasoning. If radiation pressure exceeds gravity's pull in certain regions, matter gets pushed outward instead of falling inward. That outflowing matter surrounds the black hole, with material that absorbs and scatters the light coming from deeper in. We should see dimming. We should see obscuration. We should see evidence that the black hole is choking on its own excess, hidden behind a veil of material its feeding produced. Chandra showed exactly none of that. The X-ray brightness remains strong and clear. The jets continue blasting outward with no sign of weakening. The energy signature shows matter plunging deep into the gravitational well, reaching regions so close to the black hole that the physics gets exotic even by cosmic standards. Instead of the expected obscuration and dimming, NASA's instruments captured a quasar in full display during what should be its most hidden phase. Does that seem as backwards to you as it does to the researchers analysing this data? It's like expecting a car to stall when you flood the engine, but instead it revs higher and runs smoother. The outcome directly contradicts the prediction in ways that suggest something important is missing from current understanding. The energy measurements tell part of the story. Chandra can determine not just how bright something appears, but also the character of that light, its spectrum, its variability, its polarization. Each of these properties carries information about conditions at the source, and every property Chandra measured for this quasar indicates matter falling into the black hole unimpeded by the radiation that should be blocking its path. Imagine standing near a waterfall so powerful the spray should knock you back, but instead you feel no resistance at all, despite seeing the water's enormous force. That disconnect between expected effect and actual experience would make you question your understanding of how water and force interact. Scientists face a similar disconnect here between expected obscuration and observed clarity. The jets themselves deserve attention because they represent energy that escaped the black hole's immediate vicinity and now travels across cosmic distances. These aren't gentle streams, they're concentrated flows of particles moving at substantial fractions of light speed, carrying energy equivalent to vast numbers of stars' worth of light output, sustained across timescales that span multiple human lifetimes. When astronomers detect these jets at radio wavelengths, they're seeing evidence of black hole feeding happened relatively recently, in cosmic terms. This particular quasar's jets show no sign of disruption or unusual behaviour beyond the fact they exist at all during this excessive feeding. By rights, the conditions that should obscure the central regions should also disrupt the jet formation process. Jets require specific conditions in the disk of material around the black hole, organised magnetic fields, stable inflow patterns, proper geometry. Excessive feeding that exceeds limits should disrupt those conditions, making jet formation harder or impossible. Yet the jets persist, strong and clear in observations. Another contradiction added to the growing list. Another piece of evidence that something about this black hole's feeding process differs fundamentally from what models predict. The universe is showing us reality, and reality doesn't match the script we wrote based on previous observations. Think about how humbling that is for a moment. Humanity spent decades building instruments sensitive enough to detect X-rays from objects billions of light years distant. We developed theories sophisticated enough to predict black hole behavior under extreme conditions. We tested those theories against thousands of observations and found them reliable. Then we point our best instruments at one object and discover an entire category of behavior we didn't predict and can't immediately explain. That's not failure. That's the frontier of knowledge revealing itself. The edge where certainty gives way to mystery, where textbooks need new chapters written, where the next generation of researchers will spend careers unravelling implications we can barely glimpse right now. And you're witnessing that moment in real time as NASA shares this discovery with the world. The streams of power flowing from this black hole carry more than just energy. They carry information about physics at extremes our laboratories cannot reproduce. No experiment on Earth can create the pressures and temperatures present in a black hole's feeding disk. No particle accelerator can match the energy densities. The universe provides the only laboratory where these conditions exist, and black holes like this one become experiments in natural physics that teach us what reality allows at its most extreme edges. So here's where we stand. A black hole feeding beyond predicted limits while producing energy output that should be obscured but isn't. Jets that models suggest should weaken but appear to remain steady. Brightness that should dim but stays strong. Every observation contradicts expectations built on solid previous evidence. The cosmic display continues unabated, while scientists scramble to understand what they're really seeing. And here's something that adds another layer to this mystery. This isn't happening in the universe as we see it today. This black hole exists in the distant cosmos, which means the light reaching Chandra today began its journey when the universe was substantially younger. The timeline matters because it affects what this discovery means for cosmic history and how galaxies formed during the universe's youth. But to understand why that matters, we need to look at where and when this rule-breaking giant actually exists in cosmic history. You remember looking up at stars as a child and wondering how far away they really were? That sense of vast distance hasn't changed, but our understanding of what that distance means has deepened remarkably over the decades you've been alive. When we look at distant objects in space, we're not just seeing far away, we're seeing far back in time. The light from those objects has been travelling toward us across the cosmos for so long that the universe was younger, smaller, denser when that light began its journey. This black hole sits at a distance that makes cosmic timescale suddenly very personal. The light Chandra detected didn't leave its source recently by any human measure. That light has been travelling through space for a substantial portion of the universe's total age. When those photons began their journey toward Earth, the cosmos was still in what astronomers call its youth. Galaxies were forming, stars were being born in vast numbers, and the structures we see in today's universe were just beginning to take shape. Scientists describe this cosmic distance using a measurement called redshift. Light travelling through expanding space gets stretched, shifting toward redder wavelengths in a predictable way that tells us how far back in time we're looking. This black hole's redshift places it in an era when the universe was perhaps 1/10 its current age, give or take. To put that in perspective using a human lifetime, if the universe's current age was 70 years, we're looking back to when it was around 7 years old, still very much in its developmental phase. Why does this timing matter so much? Because how quickly black holes could grow in the early universe directly affects how galaxies formed and evolved into the structures we see today. If black holes could only grow slowly, limited by the Eddington balance we discussed earlier, then reaching supermassive sizes required billions of years of steady feeding. But if they could somehow exceed those limits and grow faster, then supermassive black holes could exist earlier in cosmic history than slow growth models predict. And here's what makes this discovery particularly significant. NASA's Chandra telescope just confirmed a black hole exceeding growth limits during that early era. Not today when the universe is old and relatively quiet. During the period when everything was more chaotic, when galaxy mergers happened frequently, when star formation rates were vastly higher than anything we see in modern times. This black hole was breaking the rules when the universe was still writing those. Think about what that means for cosmic history. Every large galaxy we observe today has a supermassive black hole at its centre, our Milky Way included. These central black holes appear to play a role in regulating star formation and galaxy evolution. Their masses correlate with properties of the galaxies surrounding them. Somehow, galaxies and their central black holes evolved together, influencing each other across billions of years. But how did those supermassive black holes get so massive so quickly in the universe's youth? That question has puzzled astronomers for years, because the standard feeding limits suggest growth should take longer than the available time. If you can only gain weight at a certain rate, and you need to reach a specific size, you need enough time for steady growth to achieve that size. The math for black holes suggested they might not have had enough time to grow as large as we observe them to be in the early universe. Various theories tried to solve this puzzle. Maybe black holes formed larger to begin with, giving them a head start. Maybe they fed more efficiently than models assumed. Maybe rare conditions allowed temporary growth spurts. Each idea had strengths and weaknesses, and observations couldn't quite pin down which explanation, if any, was correct. Now Chandra hands us a direct observation of a black hole in the early universe, feeding well beyond standard limits. Not a theoretical possibility, not a maybe or perhaps, an actual measurement showing it happening. That observation doesn't solve the puzzle by itself, but it confirms that at least some black holes in the early universe could exceed growth limits we thought were universal. And that confirmation opens doors to understanding how supermassive black holes reached their enormous sizes so quickly in cosmic terms. You've watched galaxies and pictures from Hubble and other telescopes, those grand spirals and majestic ellipticals sprinkled across deep space images. Each of those galaxies formed through processes that involved its central black hole. The stars you see in those images, the structures spanning thousands of light years, the entire shape and character of each galaxy, all of it was influenced by the black hole at its heart, either feeding or resting, either pouring energy into its surroundings or sitting quiet while matter swirled. Nearby, this discovery suggests that during the formative era when those galaxies were young, black holes could grow faster than we realized, by feeding beyond limits we thought constrained them. That faster growth means more energy released during galaxy formation, more influence on surrounding gas and stars, more shaping of the cosmic structures that eventually became the galaxies we observe today, including our own. And here's where it gets personal in a way you might not have considered. The Milky Way galaxy, your home for every moment of your life, formed through these same processes. Its central black hole grew through the universe's youth, though it currently sits relatively quiet compared to the aggressive feeder Chandra observed. But during the Milky Way's formation, did its central black hole go through similar growth spurts? Did it break the same limits this distant quasar is breaking? Did it feed frantically during some ancient era, pouring energy into the surrounding gas and influencing which regions formed stars and which didn't? The stars you see overhead tonight formed from gas clouds that were shaped, in part by energy from the Milky Way's central black hole during earlier epochs. The elements in your body were forged in stars that formed in a galaxy whose structure was influenced by its central black hole's growth. The connection isn't abstract. It's written into the physical atoms that make up the world around you, including you yourself. So when NASA discovers a black hole breaking growth limits in the early universe, that's not just a distant curiosity. That's a window into the processes that formed the galactic home hosting your planet, your sun, your entire cosmic neighborhood. The mystery Chandra revealed reaches across billions of years and light years to touch the very stars you've watched throughout your life. The timing also matters for another reason. Finding this behavior in the early universe means it happened when conditions were quite different from today. The universe was denser, galaxies were closer together, gas was more abundant, star formation was more vigorous. In that environment, perhaps black holes had access to matter flows that don't exist in today's older, more settled cosmos. Maybe the rule-breaking feeding requires conditions that were common then, but rare now. If that's true, then this discovery is teaching us about cosmic evolution, showing us that the rules governing black hole growth aren't fixed across all cosmic time, but instead depend on environmental conditions that change as the universe ages. The black holes we observe nearby in today's universe might never exceed Eddington limits, simply because they don't have access to the feeding configurations that were available billions of years ago. Or maybe the opposite is true. Maybe some black holes can break these limits regardless of cosmic era, and we just happened to catch this one doing it when the universe was young. In that case, there might be rule breakers in today's universe too, waiting to be discovered once we point our instruments in the right directions and know what to look for. The mystery doesn't fully reveal which interpretation is correct yet. What we know for certain is that NASA confirmed a black hole in the early universe, feeding beyond theoretical limits, while producing energy output that defies predictions. And that confirmation came from observing an era when galaxies were forming and cosmic structures were taking shape. The implications ripple forward through billions of years to influence our understanding of how the universe evolved into what we see today including the familiar stars overhead that connect you personally to this cosmic history. But those implications grow even more profound when we consider how this discovery affects our understanding of star and galaxy formation throughout the cosmos, including the processes that led to the night sky you've known your entire life. Step outside on a clear night and look up. Those stars scattered across the darkness feel constant, like they've always been there and always will be. And in one sense that's true. The stars you see tonight are the same ones your parents saw, your grandparents saw, generations back saw when they gazed upward. But in another sense, every star up there tells a story of creation that involved black holes like the one NASA just found breaking all the rules. Here's why that matters. Stars don't form in isolation. They're born from massive clouds of gas that collapse under their own gravity. But for that collapse to happen, conditions need to be just right. Too much energy in the gas and it stays spread out, never compressing enough to ignite nuclear fusion. Too much turbulence and the cloud fragments chaotically. The process requires a delicate balance that's easily disrupted. Black holes disrupt that balance all the time, especially when they're feeding actively. Remember those jets we talked about, streams of energy blasting out along the black hole's rotation axis? Those jets slam into surrounding gas clouds with tremendous force. Sometimes that force triggers new star formation by compressing gas. Sometimes it heats gas so much that star formation shuts down entirely. The black hole at a galaxy's centre becomes a thermostat, controlling when and where stars can form throughout the entire galaxy. Now think about what Chandra revealed. A black hole feeding well beyond expected limits, producing energy output that exceeds predictions, maintaining brilliant brightness when it should be dimmed. All that excess energy has to go somewhere. It pours into the black hole's cosmic neighbourhood, heating gas, pushing material around, influencing structure across distances spanning the entire galaxy and beyond. In the early universe, when this black hole was doing its rule-breaking feeding, galaxies were forming at rapid rates. Star formation was far more active than in today's older cosmos, and black holes like this one were pumping enormous energy into their surroundings during that crucial formative period. The energy they released shaped how gas could flow and where stars could form, essentially sculpting the structure of young galaxies during their most critical development phase. Those young galaxies eventually evolved into the mature galaxies we see today when we look at the nearby universe. The Milky Way was once a young galaxy undergoing rapid star formation. Andromeda was forming through similar processes. Every galaxy visible in modern telescopes passed through an early phase where central black holes were growing and releasing energy that influenced their development. And here's the connection that makes this personal. The Sun formed from a gas cloud in the Milky Way's disk about 5 billion years ago. That gas cloud existed because the Milky Way's structure allowed it to exist, because gas flows in our galaxy followed patterns shaped by earlier black hole activity and star formation across billions of years. The very fact that your Sun formed where and when it did connects back to processes involving our galaxy's central black hole during earlier epochs. Could the Milky Way's central black hole have gone through similar rule-breaking growth phases? Could it have exceeded Eddington limits during some ancient era, pumping extra energy into its surroundings, influencing gas flows in ways that eventually determined where stars like the Sun would form billions of years later? We don't have direct evidence of that, but Chandra's discovery shows such behaviour is possible for black holes in the early universe. And the Milky Way's black hole was certainly present and growing during that era. Think about the chain of connection reaching from that distant quasar to the stars above your house tonight. Black holes in the early universe grow beyond expected limits. That growth releases enormous energy. The energy shapes gas flows and star formation. Galaxies form structures influenced by that energy. Billions of years pass. Those young galaxies become mature systems. Stars form in patterns influenced by the ancient structure. One of those stars is your Sun. Planets form around it. Life emerges on one planet. And you stand here now, looking up at the result of billions of years of cosmic evolution that included black holes breaking rules we're only now beginning to understand. That's not poetic exaggeration. That's the actual chain of physical causation, connecting distant cosmic events to your immediate reality. The universe is not separate compartments with black holes over here and life over there. It's an interconnected whole, where processes at the largest scales shape conditions at smaller scales, eventually influencing everything down to the planet beneath your feet. The discovery also affects how we interpret the night sky itself. Those stars overhead exist in specific patterns, constellations you've known since childhood, clusters and nebulae visible through telescopes, the band of the Milky Way stretching across dark skies. All of that structure came from processes involving black holes growing at galaxy centers and influencing their surroundings. If black holes can grow faster than we thought by exceeding theoretical limits, then the timeline and energy budget for galaxy formation needs rethinking. Maybe stars formed faster in certain regions because black holes pumped more energy into those areas than models predicted. Maybe other regions stayed dark longer because excessive black hole activity suppressed star formation more effectively than we realized. The detailed history of how our galaxy became the structure we observe today depends on understanding what its central black hole did during the formative epochs, and Chandra just showed us that black holes in that era could behave in ways our models didn't predict. You know that sense of continuity you feel when you look up at familiar stars? That connection to the past, knowing your ancestors saw those same points of light? Well, the cosmic past extends much further back than human history, and it's more dramatic than stories told around campfires. Those stars are the surviving products of billion-year processes involving catastrophic explosions, galaxy collisions, and yes, black holes feeding at rates that break textbook rules. You're not just looking at peaceful, unchanging lights. You're seeing the outcome of cosmic violence and growth that shaped the entire structure of your galactic home. And here's something worth considering. If one black hole in the early universe could exceed limits so dramatically, how many others did the same? Were there hundreds or thousands of rule breakers pumping extra energy into the forming universe? Or was this one an unusual exception, a cosmic outlier that we happened to catch during a rare extreme phase? The answer affects our entire picture of cosmic evolution and how the universe transitioned from its hot, dense youth to the cooler structured cosmos we inhabit today. NASA's discovery doesn't answer that larger question yet, but it confirms such behaviour happens, and happened when it mattered most for structure formation. That confirmation changes the conversation among researchers studying how galaxies evolved. Now they have to account for the possibility that black holes exceeded standard growth limits during crucial epochs, releasing more energy and influencing their environments more dramatically than conservative models assumed. The familiar stars overhead suddenly carry a deeper story. They formed in a galaxy whose structure was shaped by processes we're still working to understand. Processes that included black hole growth beyond predicted limits during the universe's formative centuries of millions of years. And every time you look up at that night sky, you're seeing physical evidence of cosmic history that reaches back to the era Chandra is now revealing through this remarkable discovery. But understanding how significant this discovery really is requires hearing from the people who actually made it. The researchers who pointed Chandra at this distant quasar analysed the data and realised they were looking at something that shouldn't exist according to current theories. Their voices, their reactions, their honest admission of bafflement give us the clearest picture of why this matters so profoundly. You've watched enough press conferences and interviews to know when experts are reading from scripts versus when they're genuinely surprised. The difference shows in their tone, their word choices, the way they pause to find the right phrase for something they're still processing themselves. NASA's team analysing this discovery falls squarely into the genuinely surprised category. These are veteran researchers who've spent careers studying black holes, and the data from Chandra has them openly admitting they don't understand what they're seeing. Listen to how they describe it. When the lead researchers discuss this black hole's behaviour, words like shocking and unexpected appear repeatedly. Not in the overblown way those terms get thrown around casually, but with the weight of scientists confronting observations that challenge fundamental understanding. One researcher noted that finding a black hole exceeding the Eddington limit to this degree was completely unanticipated based on current models. That's not hedging or downplaying, that's straight acknowledgement that reality surprised them. Think about what it takes for NASA scientists to make statements like that publicly. These are people trained to be cautious about claims, careful about distinguishing between observation and interpretation, aware that their words carry institutional weight. When they come forward and essentially say we found something we can't explain with existing physics, that's a significant admission reflecting genuine scientific mystery rather than hype for public attention. The research team includes experts from the Center for Astrophysics, an institution with decades of credibility in studying high-energy cosmic phenomena. These aren't newcomers making bold claims hoping to make names for themselves. These are established researchers putting their reputations behind observations that fundamentally challenge accepted models. That level of confidence in the data, despite its implications, tells you the observations passed every check they could throw at them. One particularly revealing aspect of their discussion involves how clearly the data shows the black hole exceeding limits during a phase when it should be most constrained. The researchers point out that the observations leave little room for alternative interpretation, the energy signatures are unambiguous, the feeding rates are measured directly from the spectrum, and the brightness speaks for itself. When scientists this experienced say the data is clear, that's high confidence in the measurement itself, even while acknowledging confusion about what the measurement means. There's something refreshing about hearing experts admit uncertainty while maintaining confidence in their observations. It reflects how science actually works rather than the cartoon version, where researchers either have all the answers or doubt everything. Real science involves moments like this, solid measurements that don't fit current understanding, requiring new thinking rather than dismissing either the observation or the previous theory wholesale. The team's commentary also reveals the thought process behind the discovery. They weren't hunting for rule-breaking black holes specifically. They were conducting routine observations as part of ongoing surveys, mapping out quasar properties across cosmic time. This black hole stood out in their data unexpectedly, prompting deeper analysis that confirmed the anomalous behaviour. That element of surprise reinforces the authenticity. This wasn't a case of looking for something specific until they found it. This was reality asserting itself into data they were collecting for other purposes. You remember moments in your own life when you stumbled onto something unexpected while doing routine tasks? When reality surprised you by not matching assumptions? That's the flavour of this discovery from the researchers' perspective. They were mapping the universe, checking boxes, expecting data to fit patterns established by thousands of previous observations. Instead, they got this outlier demanding explanation and offering none that fits comfortably within existing frameworks. The researchers' willingness to engage with the mystery publicly also matters. They've presented findings at conferences, published papers, discussed results with colleagues worldwide. That openness invites scrutiny and alternative interpretations, which is exactly how science should handle surprising discoveries. If they weren't confident in the data quality, they'd keep things quiet until they verified every detail multiple times. The fact they're discussing it openly signals they've already done that verification and stand behind the observations. One aspect that comes through clearly in their descriptions is the systematic ruling out of alternative explanations. Could the quasar's brightness be explained by something other than excessive feeding? Could the measurements be affected by intervening material between the quasar and Chandra? Could instrumental effects create false readings? The team addressed each possibility methodically and found no alternative explanation that accounts for what they're seeing. That elimination process strengthens confidence that the mystery is real rather than a misinterpretation. The human element of discovery shows through in these discussions too. You can sense the mixture of excitement and frustration. Excitement at finding something genuinely new. Frustration at not having ready explanations for it. That's the emotional reality of frontier research. Every career scientist hopes to find something unexpected that advances understanding. But when you actually find it, the path forward isn't immediately clear. You have a puzzle without an obvious solution, requiring hard work and creative thinking to make progress. Some researchers on the team are focusing on alternative feeding mechanisms that might allow black holes to exceed standard limits. Others are examining whether the quasar's environment has unusual properties that change how radiation pressure works. Still, others are considering whether theoretical models need fundamental revision rather than just parameter tweaking. The diversity of approaches reflects healthy scientific process, multiple smart people attacking the problem from different angles to see which line of investigation bears fruit. There's also a generational aspect worth noting. Some team members were students when Chandra launched, now mid-career researchers, using data from instruments they watched being built. Others are senior scientists who remember when detecting quasars at all was cutting edge, now confronted with observations sophisticated enough to reveal detailed behaviour those early discoveries couldn't measure. The multi-generational nature of this work connects your lifetime of watching space exploration to the current frontier of cosmic discovery. The researchers emphasise that solving this mystery will require additional observations, not just more analysis of existing data. They're advocating for follow-up observations with other instruments that can measure different properties of this quasar and similar objects. That call for more data reflects scientific humility, acknowledging that understanding will come from accumulating multiple perspectives on the phenomenon rather than one team having a sudden breakthrough insight. When you listen to these scientists discuss their findings, there's no sense of defensive protection of previous ideas or dismissal of challenges to established theory. Instead, there's genuine curiosity and eagerness to figure out what's really happening. That attitude is what allows science to progress when faced with observations that don't match predictions. The willingness to say our models appear incomplete opens the door to improving those models rather than forcing reality to fit outdated frameworks. The team's work represents decades of collective experience suddenly confronting something that experience didn't prepare them for. That moment of encountering the genuinely new, when expertise reveals its limits and humility becomes essential, that's where discovery happens. And you're witnessing that moment through their words as they share this cosmic mystery with the world. Their honesty about not having answers yet is precisely what makes their confidence in the observations credible. They're not selling certainty they don't possess. They're sharing a genuine puzzle and inviting broader engagement with it. That approach reflects the best traditions of scientific inquiry, going back to when humans first looked up at stars and wondered what they were seeing. The tools have become incomparably more sophisticated, but the fundamental posture, honest observation coupled with humble admission of what we don't yet understand, remains the same. And what comes next, according to these researchers, involves pointing humanity's next generation of telescopes at similar objects to see if this behaviour is rare or common, temporary or sustained, limited to specific cosmic epochs or present throughout cosmic history. That investigation is already beginning, building on Chandra's discovery to expand our understanding of how the universe actually works at its most extreme edges. You've watched technology advance throughout your lifetime at a pace that would have seemed magical to earlier generations. Telescopes have followed that same arc of improvement, from ground-based instruments peering through Earth's turbulent atmosphere to space observatories detecting wavelengths invisible to human eyes, revealing cosmic landscapes previous generations could never have imagined observing. Chandra X-ray Observatory launched back when many current researchers were just starting their careers. For over 2 decades, it's been scanning the high-energy universe, mapping hot gas, detecting black holes, revealing violent cosmic processes invisible to optical telescopes. The discovery we've been discussing showcases Chandra working exactly as designed, detecting faint X-ray emissions from objects billions of light-years distant, and turning those detections into precise measurements that challenge our understanding. But Chandra is part of a larger ecosystem of observatories, each designed to observe different aspects of the cosmos. James Webb Space Telescope operates in infrared wavelengths, peering through dust that blocks visible light, seeing objects so distant their light has been shifted completely out of optical ranges. Other instruments specialize in radio wavelengths, or gamma rays, or the entire electromagnetic spectrum. Together, they provide multiple perspectives on cosmic objects, like observers surrounding a sculpture, and each describing what they see from their unique vantage point. This black hole mystery highlighted by Chandra now becomes a target for follow-up observations with complementary instruments. James Webb can look at the same region and see different aspects, perhaps detecting the galaxy hosting this black hole, measuring its properties, determining whether anything unusual about the environment might explain the anomalous feeding behaviour. Radio telescopes can map the jets in greater detail, tracing their structure across vast distances, looking for clues about what's driving them so powerfully during this excessive growth phase. Each new observation adds pieces to the puzzle. Maybe infrared data will reveal massive gas streams flowing toward the black hole along unexpected paths. Maybe radio observations will show asymmetries in the jets suggesting unusual feeding geometry. Maybe additional X-ray monitoring will catch changes over time that reveal patterns not visible in single snapshots. The process is methodical: accumulate observations, test hypotheses, refine understanding step by step. And here's what makes this an exciting time despite the mystery. We have the tools to actually investigate cosmic puzzles at this level of detail. 30 years ago, detecting this quasar at all would have been an achievement. Measuring its basic properties would have been cutting edge. Today we can not only detect and measure, but characterize its behavior in enough detail to recognize when something doesn't match predictions. That capability is what allows science to progress beyond confirming what's expected into discovering what's genuinely new. The next generation of instruments currently in planning stages will push these capabilities even further. Proposed X-ray observatories with higher sensitivity could detect fainter sources or measure brighter ones with greater precision. Advanced radio telescope arrays will map jets and surrounding structures in unprecedented detail. Each improvement in technology opens new windows for discovery, revealing aspects of the cosmos we couldn't access before. Think about the trajectory you've witnessed. When you were young, black holes were theoretical curiosities, mathematical solutions to Einstein's equations that might or might not exist in reality. By the time he reached middle age, evidence for black holes had become overwhelming. Now in recent years, we've actually captured images of black hole shadows and measured gravitational waves from black hole collisions. The progression from theory to confirmed reality to detailed characterization happened within a single human lifetime, yours. This discovery about rule-breaking feeding represents the next step in that progression. We're not just confirming black holes exist, or measuring their masses. We're detecting behaviour subtle enough to reveal gaps in our understanding of how they work. That level of sophisticated investigation only becomes possible with the accumulated improvements in telescope technology and data analysis techniques developed across decades of patient work. The researchers studying this mystery aren't working in isolation either. They're part of a global community sharing data, comparing observations, building collaborative understanding. When Chandra detects something unusual, scientists worldwide can request time on other telescopes to follow up. That collaborative ecosystem accelerates progress in ways that weren't possible when research was more siloed and proprietary. And the pace of discovery is increasing. Each year brings new observations from the current generation of telescopes, while new instruments come online or reach full operational capability. James Webb continues revealing distant galaxies and cosmic phenomena barely imaginable before launch. Ground-based observatories push their capabilities through advanced adaptive optics that compensate for atmospheric distortion. The volume of cosmic data available to researchers grows exponentially, and within that flood of information, more mysteries like this one wait to be recognized. You might wonder whether all these future observations will solve the puzzle Chandra revealed, or just deepen the mystery further. Honest answer, probably both. Additional data might explain how this particular black hole exceeds limits, but in the process of explaining that, researchers might discover new puzzles and unexpected phenomena requiring their own investigation. That's how science actually progresses, not solving everything and reaching final answers, but expanding understanding in ways that reveal new frontiers worth exploring. The timeline for understanding this black hole's behaviour isn't immediate. Science doesn't work on schedules dictated by impatience or curiosity alone. It works on the timescale of careful observation, thoughtful analysis, peer review, and collaborative refinement. This mystery might find satisfying explanation in a few years as more data accumulates, or it might take a decade or more as theoretical frameworks get tested and revised. The important thing is the investigation continues, driven by genuine curiosity about how the universe actually works. There's something hopeful in that process. The idea that human understanding can expand to encompass even genuinely surprising observations. We're not stuck with the knowledge we have today. The frameworks that seem incomplete right now can be improved and refined as observations reveal what's missing. That potential for growth applies to scientific understanding the same way it applies to personal growth throughout life. You'll never finish learning if you remain open to being surprised by reality. The telescopes chasing answers to this mystery are extensions of human curiosity pointed at the cosmos. Every instrument represents decades of engineering work, millions of hours of collective human effort, and the determination to see what's really out there rather than just what we expect to find. That determination is what allows discoveries like this to happen in the first place. The willingness to point instruments at the sky and record what they reveal, even when it contradicts comfortable assumptions. And as those instruments gather new data on this black hole and others like it, the cosmic story becomes richer and more nuanced. We move from simple models that worked for initial understanding toward more complete frameworks that account for exceptional behaviour and edge cases. The universe reveals itself as more interesting than our first-pass theories suggested, which is exactly what you'd hope for if reality is richer than human imagination alone could construct. So while this particular mystery remains unsolved for now, the trajectory is clear. More observations are coming, more analysis will follow, more researchers will engage with the puzzle, and gradually, understanding will expand to encompass this black hole's rule-breaking behaviour along with whatever other surprises await discovery in the data yet to be collected. That's the process you're witnessing. Science working exactly as it should, following evidence wherever it leads, building toward more complete knowledge of the cosmos we inhabit. And that process connects directly to something you can do tonight: step outside, look up at those familiar stars, and recognise that the universe above you is more mysterious, more dynamic, and more surprising than any generation before yours had the tools to fully appreciate. The cosmic adventure continues, And you're alive at precisely the moment when humanity's instruments are sophisticated enough to detect phenomena our ancestors couldn't have imagined. That's a remarkable position to occupy, and it leads naturally to one final reflection about what this discovery means for how we see our place in the universe. You've stood under these same stars for decades now, watching them wheel across the sky through seasons and years. Those patterns became familiar friends, constant companions on clear nights, when you took time to look up and remember the larger cosmos beyond daily concerns. And part of what makes those stars comforting is their apparent permanence, the sense that they're unchanging anchors in a universe that otherwise moves too fast. But here's what NASA's discovery invites you to reconsider. Those stars might look permanent from a human lifetime's perspective, but each one tells a story of violent birth, sustained nuclear fury, and eventual dramatic death. The black holes those deaths sometimes create go on to shape the next generation of star formation through their feeding and energy release. And now we know that at least some of those black holes, especially during the universe's youth, fed beyond limits we thought were absolute, pumping extra energy into their surroundings and influencing cosmic evolution in ways we're only beginning to understand. That doesn't make the stars less comforting. If anything, it makes them more remarkable. You're not just looking at static points of light. You're seeing the survivors and descendants of billion-year processes involving catastrophic events and rule-breaking cosmic giants. Every star overhead exists because the universe's history unfolded in specific ways we're still working to fully understand, but ways that included black holes behaving more dramatically than initial theories predicted. Think about what it means that the universe can still surprise us this way. Humanity has been studying the sky for millennia, applying scientific instruments to those observations for centuries, and using sophisticated space telescopes for decades. Yet, we just discovered a category of black hole behaviour that challenges fundamental physics. The cosmos keeps secrets well, revealing them only when we develop instruments sensitive enough and minds open enough to recognise what we're seeing. That capacity for surprise suggests humility should temper confidence. Yes, we understand an enormous amount about how the universe works. The models explaining cosmic evolution from the Big Bang to today stand on solid observational evidence, but this discovery reminds us that our understanding, while substantial, remains incomplete. There are phenomena we haven't fully characterized, behaviors we haven't perfectly predicted, cosmic processes operating according to rules we've yet to articulate completely. And that's exciting, rather than discouraging. It means there's more to discover, more to understand, more opportunities for reality to teach us about itself. The universe you're looking at tonight is demonstrably more interesting than the universe described in textbooks from even 20 years ago. And the universe that will be described in textbooks 20 years from now will likely incorporate understanding we don't have yet, built on discoveries not yet made, answering questions we haven't fully articulated. You're living through a remarkable era for cosmic discovery. The tools exist to probe the universe's secrets at unprecedented depth. The collaborative networks allow rapid sharing of findings and coordinated follow-up observations. The public communication channels let you witness discoveries almost in real time, rather than learning about them years after the fact through filtered summaries. This immediate connection to frontier science was impossible for most of human history. The fact that you can know about NASA's black hole discovery within months of the observations being analysed represents a profound democratization of knowledge. That access carries responsibility too, the responsibility to appreciate what's being discovered without demanding more certainty than observations justify. Science works by accumulating evidence and refining understanding over time. The process requires patience to let investigation unfold naturally, rather than rushing to conclusions that feel satisfying but might not reflect reality accurately. This black hole mystery won't be solved tomorrow or next week, but it will be investigated thoroughly, and eventually the pieces will fall into place through persistent, careful work. In the meantime, the mystery itself has value. It reminds us that the universe operates according to its own principles, regardless of human understanding. Black holes don't check our textbooks before deciding how to behave. They follow physics faithfully, even when that physics includes subtleties we haven't incorporated into our models yet. Discovering those subtleties is how science progresses from approximate understanding to more complete knowledge. So when you look up tonight and see those familiar stars, let NASA's discovery add a layer to your appreciation. Those stars formed in a universe where black holes sometimes break the rules, where cosmic evolution followed paths more complex than simple models suggest, where reality proved richer than our initial theories anticipated. The cosmos you're gazing at is not just vast and ancient, It's genuinely surprising in ways that reward careful attention and patient investigation, and maybe that's the most profound takeaway from this entire cosmic detective story. The universe doesn't exist to make sense to us, or to follow rules we find convenient. It exists according to its own nature, and that nature turns out to include black holes that can somehow exceed limits we thought were absolute. Understanding how they do that will require work, creativity, and willingness to revise ideas when evidence demands it. But that work is happening right now, carried forward by researchers who saw something unexpected and chose to investigate rather than dismiss it. You're part of that story too, not just as a spectator, but as someone whose tax dollars fund NASA's telescopes, whose interest justifies continued space exploration, whose sense of wonder motivates the next generation to pursue careers unravelling cosmic mysteries. The connection between you looking up at stars from your backyard and researchers analysing black hole data from Chandra is real and meaningful. We're all participants in humanity's ongoing conversation with the cosmos, asking questions and listening for answers written in light across billions of light years. The black hole that prompted this conversation will continue feeding and glowing billions of light years away whether we understand it or not. But through patient observation and careful thought, that understanding will grow. And when it does, we'll see not just that one black hole more clearly, but the entire universe with fresh eyes, recognising patterns and processes we missed before, appreciating the cosmos as it actually is, rather than as we initially imagined it to be. That journey from observation to understanding to deeper mystery to expanded knowledge is the heartbeat of science itself. And you've just witnessed one complete cycle of that heartbeat. NASA observed something unexpected, announced it honestly, and now the scientific community engages with the mystery to deepen understanding. That cycle will repeat countless times throughout the rest of your life and beyond, each iteration revealing new facets of the universe above your head. So I'll leave you with this invitation. Tonight, when you step outside and look up at those familiar stars, pause for a moment to appreciate everything they represent. The vast cosmic history stretching back to the universe's youth, the black holes that shaped galaxies during that history, sometimes breaking rules we thought were absolute, the ongoing human effort to understand all of it through careful observation and honest investigation, and the simple fact that you're alive at exactly the moment when our species developed tools powerful enough to detect cosmic mysteries like this one. The stars are waiting for you, carrying secrets we're still learning to read, and the universe continues its grand performance, whether we watch or not. But watching makes us part of the story, connecting our brief human lives to cosmic narratives spanning billions of years. That's a remarkable connection to possess, and it's available to anyone willing to look up and wonder at what they're seeing. If this journey through cosmic mystery helped you see the night sky differently, do me a favour. Hit that like button so others can discover this story too. And drop a comment telling me where you're watching from under tonight's stars. I love hearing from viewers all over this planet we share under this cosmos we're all exploring together. The universe, just revealed, it's more mysterious than we knew. Let's keep looking up together to see what else it has to teach us.